Hello guys, in this video I'm going to explain how Prim's algorithm works. Okay, so first we understand what is Prim's algorithm and why we use Prim's algorithm. So Prim's algorithm is a greedy algorithm used to find a minimum spanning tree. Means we use Prim's algorithm to find minimum spanning tree for a connected, weighted and undirected graph. Basically, we use Prim's algorithm to find MST. In my last lecture, I also explained Kruskal algorithm, which we also used to find the minimum spanning tree. The answer of both the algorithm is same, but they have different working flow. Okay, now come to what is the output of Prim's algorithm. The output of Prim's algorithm is a minimum spanning tree. Now first we learn what is minimum spanning tree. So a spanning tree is a subgraph of a graph. Means it is a smaller version of a graph. If we have given a graph G and it has vertices E and edges E. Okay. So a minimum spanning tree contain all the vertices of G. Means in a spanning tree vertices are equal to V. Means all the vertices in graph. Okay, and it must be connected like we can reach all the vertices with each other in the spanning tree or minimum spanning tree. No cycles means there is no cycle. Okay, now this is the important point for the minimum, because we have to make a minimum. Okay, so minimum spanning tree has must have minimum weight. Means when we sum all the weights of edges in the minimum spanning tree, it must be minimum. Okay, now come to how Prim's algorithm working of Prim's algorithm. First, initialization means we start from a random or arbitrary vertex. If the starting vertex is given in the question, then you can start from that vertex. Otherwise, you can start from random vertex. Okay, and add it to the minimum spanning set. Okay, I will also explain the working with the example. Okay, find minimum edge. Now, among all the edges that connects a vertex in the MST set to be a vertex outside the MST set, select the one with the minimum weight. Means suppose we have a vertex A and it connected to 3 and 5 is given. So in our this is our minimum. Okay, so in our minimum tree, suppose we start from this. suppose we start from A, so we have to find the minimum from these. Okay, now minimum will be this, so we draw like this is B, C, D. So we choose the minimum weight edge. Okay, and then we expand our minimum spanning tree, add the selected edge and the new vertex to the MST set. Okay, now as you can see in our minimum spanning set, first we have only the vertex A, and after finding the minimum edge, we add it to our MST and also the new vertex. Okay, now repeat. Continue steps 2 and 3 until all vertices in the graph are included in the MST set. Okay, you have to repeat the step 2 and 3. Like here, we have to find the all the edges which are connected to B, then find the minimum one, then connected it to a B. You must follow these process until all the vertices are included in the MST, because as I already explained, a minimum spanning tree is a spanning tree who contain exactly V vertices. Means a minimum spanning tree must have equal number of vertices. So when our vertices are equal, then we simply say that our minimum spanning tree is complete. Okay, now I'm explain how the Prim's question is to be solved. So in this question, basically a graph is given to us and we have to find the minimum spanning tree. Okay, so in Prim's algorithm, as I already told you, we can start from arbitrary vertex. Okay, arbitrary means you can start from a random vertex. In the case when given vertex is not provided in the question. Okay, or there is no vertex given in the question. Okay, suppose we start from A with node A. Okay, so you have to write the starting node. Okay, now find all all the edges connected to this vertex. Okay, now this and this are connected. Okay, so in rough side or in your rough copy, simply write 7 and 8. Okay, and select the edge which have minimum weight. So here 7 is the minimum weight. Okay, so simply draw 7 weight edge. Okay, but before adding the edge, ensure that it do not make any cycle. Okay, okay, now okay, now add the edges which have weight and connect it to the new vertex, and our new vertex is B, and find all the connected edges to it. Okay, so what is connected edges? One is 3, one is 6, and we already use this edge, so we are not going to include it this edge again. Okay, this is already included, this is also already included. Okay, now add these edges into our rough page. Okay, so 8, 3 and 6. Now find the minimum one. Here the minimum is 3. Okay, so draw the minimum weight edge. Okay, now write all the edges connected to the new vertex, which is C. Okay, so our new vertex is C, and all the edges, one is weight edge. We already take this. We already take this. Now these are new one. Okay, so add 4 and 3 again. Okay, now I have to mention an important point where students generally make the mistake. Okay, at this point, student consider the new edges. Consider new edges weight, but they forgot the old weights edges. We have to find the minimum from the new one also, and the previous or old one which we not take because of the large weight. Okay, so remember this point. Remember this. Okay, now find the minimum edge. Minimum edge is 3. Okay, check 3 make any loop or cycle? No. 3 no, do not make any loop or cycle. Okay, now add all the edges of 3. Okay, now the edges which are connected to vertex E are 2 and 2. Okay, this 2 and this 2. Okay, now the minimum one is, suppose we take 2 and this is a 2. So add this. But keep in mind it add this because it not make any cycle. Okay, if this make the cycle, then I'm not include this in my MST. Okay, now add all the edges which are connected to D. Now 6 4, I already use this 6, I already use this 4. When we take vertex C, we include this into our weights edges. Now add the new edges which are connected to D to our left side. Okay, now we already use this, we already use this, we already use this, and the edge which have weight 5, we include this. Now again find the minimum weight edge. So the minimum weight is 2. Okay, so we again add this because it don't make any cycle. Okay, now add the edges which are connected to vertex F, basically is 5, but we already use 5. Okay, that's why we are not going to add the edge 5 again to our rough side. Okay, so find the minimum one. Now the available weights are these, and the minimum is 4. Now if I add weight 4, it will make a cycle. Even this is the minimum weight edge, but still we are not going to add this into our MST because it forms the cycle. And as we discussed, spanning tree do not contain any cycle. Okay, that's why we are not include this. Okay. Remember this point. Now we have available weights are this, and find the minimum weight. Okay, the minimum weight. Now same here, if I add this weight, so it will make the cycle, as you can see clearly. Okay, this is the basically cycle. That's why I'm not include the edge which have weight 5 also, or weight 5 edge. Okay, now remove 5. We have available weights 8 and 6. Okay, so if we add 6, then here also 6 also make the cycle. Okay, so we do not include this. So remove this from our available edges, and now our last and remaining edge weight is 8. Okay, now check where 8 is present. 8 is present here. If I connect this, it also make the cycle. That's why I'm not include this in my MST. And also an important point which I'm going to tell is the intermediate result of Prim's algorithm is connected. Means when we check the in between result as we form, and we are making the MST, the MST is connected, while in Kruskal it is disconnected. In Kruskal, in Kruskal, this is disconnected. Okay. Now this is our minimum spanning tree. Okay, now what is the cost of the minimum spanning tree? The cost of the spanning tree is the sum of all the edges weight in the minimum spanning tree. Okay, so 7, this one, then 3, then 3, then 2, then 2. Okay, now calculate this. 7, 3, 10, 10, 5, 15, 15 to 17. So our minimum spanning tree weight is 17. Okay, and you can check you make the spanning tree correct or not by counting the vertices, the number of vertices, the number of edges. Okay, so in our graph we have total number of vertices 1 2 3 4 5 6. We have total number of vertices 6. Okay, and in spanning tree we also have equal number of vertices. We have to check this. 1 2 3 4 5 6. Okay, so here 6 also. This condition is satisfied. And how many edges we must have in Prim's? Okay, so v minus 1 is 5. We must have 5 edges in the minimum spanning tree. 1 2 3 4 5. So this is our minimum spanning tree. Okay, now come to the time complexity of the Prim's algorithm. The time complexity of Prim's algorithm is big O of v plus e into log v, where v belongs to vertices and e belongs to edges. Okay, now come to the applications of Prim's algorithm, where we use the Prim's algorithm in real world or our daily life. We use Prim's algorithm in network design. Okay, minimizing the amount of wire needed to connect a set of locations. Basically, we use the Prim's algorithm to reduce the cable wire amount. In circuit design also we use the Prim's algorithm to reduce the circuit minimal wire length, or to reduce the length of the wire we use in integrated circuits. Okay, design integrated circuits to connect all terminals with minimal wire length. Basically, we we use Prims where we have to reduce either length, cost, distance. Okay, basically. So I hope this will help you guys. Okay, so please like, subscribe my channel. Okay, because it will motivate me.